Let's look at several key places on phase diagrams and an idea about navigating our way around different phase diagrams for pressure and temperature changes. So the following shows a generic phase diagram for a pure substance where we see the solid is most stable at low temperatures and high pressures, and the gas is at high temperatures and low pressures, and the liquid exists somewhere in between. The lines on the diagram are what we'll call the equilibrium lines between two phases. So along these lines we have the two phases at the boundaries existing in equilibrium. That means at those temperatures and pressures, those two phases have the same free energy. So one is not more stable than the other, and they coexist. You can transfer between one or the other by adding energy, because the liquid will always be higher in energy than the solid. But the two have the same free energy. So for instance, a glass of ice water sitting on the table will have ice and liquid, and they will coexist. For the ice to melt, you have to input some heat. But if you don't put energy in or take energy out, the amount of solid and the amount of liquid will stay the same. So the one melting line is the equilibrium between the solid and the liquid. The two gas lines, the equilibrium point between the solid and the vapor and the liquid and the vapor, show the vapor pressure of the liquids and the solids at different temperatures. The other key point is the triple point. And here we have the triple point between the solid and the liquid and the gas. And at this point, all three phases exist in equilibrium, and they all have the same free energy. The solid, the liquid, and the vapor, and here you'll see the solid and the liquid obviously have the same vapor pressure. Otherwise, the vapor pressure of the solid is always lower than the vapor pressure of the liquid. They're equal at the triple point. So one other key point is the critical point. So the liquid vapor line doesn't just end because we're lazy, it ends because the definition of a liquid and a vapor disappear at that point. If you imagine what's happening is we're cranking up the temperature and the pressure following that line, the gas is getting more and more dense, and the liquid is getting less and less dense, and finally you get to the point where actually the density of the two phases merge, and you end up in one new phase. And this new phase we call a supercritical fluid, and the supercritical fluid is neither gas nor liquid. It is possible to get from a liquid to a gas without undergoing a phase change by going up and around the critical point. That is, we never cross over the place of the equilibrium boundary line where there's still a distinction between the liquid and the gas. So there's no phase boundary between a gas and a supercritical fluid or a liquid and a supercritical fluid. Those are continuous changes in density. So let's think about what happens as we move across this diagram, starting out in a pure liquid state and going over to a pure gaseous state. So at point 1, we have a sample that's all liquid. And now you can imagine as you raise the temperature up and up and up and up, the liquid expands a tiny bit, but not very much, because liquids tend not to have big density changes with temperature. But we finally get to the equilibrium point, and at point 2, we discover that gas starts to form. And we can try to change the temperature, but instead the temperature's not changing. The energy that's going in is going into the phase change, and we get liquid and gas. And as we sit there, we can continue to try to input more energy, and we'll get to the third point. The third point is still on the phase boundary. Now we have just a little bit of liquid left, but we're generating more and more and more gas. And finally we get to the point where all of the liquid has turned into a gas, and now as we input energy, the temperature is increasing and the volume is increasing, and we end up in a situation that's all gas. So it's important to remember that on the phase boundary, we can have all liquid with one bubble of gas or all gas with one drop of liquid. We just need to have the two phases both present, but we could have any amount of either. The thing that's fixed is the pressure. The pressure of the gas at that point has to be the same, or we wouldn't be on the equilibrium line. So a typical phase diagram for a substance, 1 atmosphere lies about where it does on this graph. That is, an atmosphere is a place where we can have both solid and liquid and gas. This would be a substance which wouldn't sublime at an atmosphere because the sublimation points are all down below this. If we look at these two lines, we see we have the vapor pressure of the solid and we have the vapor pressure of the liquid. And if we look at where 1 atmosphere intersects these lines, we see that where it hits the melting point curve is the normal melting point. That is, what is the temperature at which there's an equilibrium between the solid and the liquid at 1 atmosphere. And the normal boiling point is where the vapor pressure of the compound is equal to 1 atmosphere. So let's look at a typical phase diagram for a substance we know, CO2. You can see CO2 doesn't quite fit the diagram that I just showed because 1 atmosphere is now down below the triple point. So since we're usually working at 1 atmosphere, that means there isn't any temperature at 1 atmosphere pressure that liquid CO2 is stable. Either we have a solid or we have a gas, and that's why for CO2, at 1 atmosphere pressure, it sublimes. And if we have a hunk of dry ice, which is solid carbon dioxide, it will have a temperature of minus 78.5 degrees Celsius because it will be constantly subliming until it turns up into a gas and then the gas warms up. You can also see the supercritical fluid region on this is at a pressure of about 73 atmospheres and a temperature of only 31 Celsius. And that means that CO2 is a compound that's fairly easy to turn into a supercritical fluid because while the pressures are fairly high, the temperatures aren't very extreme. Water is a very important substance, and there's one key thing to think about when we think about what's different with water in a phase diagram. The key difference here is that the solid-liquid line actually tilts the other direction. That is, as you increase the pressure, you lower the melting temperature. And this is very strange, and we wouldn't talk about it at all, except that water is a compound that's very important. And the reason is that liquid water is actually more dense than solid water. Ice floats in liquid water. It's very strange. None of us think it's strange because we see it all the time, but it's really weird that the solid has a lower density than the liquid. And so now as we raise the pressure up, like the arrow shows on the diagram, what happens? We're squeezing the solid and it's going to move into the more dense phase, which means if we fix the temperature and crank the pressure up, we eventually end up as a liquid. Normally, you would be in a liquid, the lower dense phase, and as you raise the pressure, you would end up as a solid. But water is a little bit of an oddball. The other thing that's interesting to note is you can look at just where the triple point is for water. The triple point for water is almost exactly the normal freezing point. The triple point is just a fraction above 0 degrees Celsius. And it has a pressure that's somewhere close to an atmosphere. This is the full phase diagram of water. And the thing to note here is that there are many, many, many forms of solid water. So phase diagrams can be very complicated because you can have many different forms of a solid. Solids can form as amorphous substances or in different crystalline forms, and they will exist at different places on the phase diagram. And all of the phases here, noted with little Roman numerals, are different solid phases of water. There are many different forms of ice. And one thing that's useful to note is that up at the top of the diagram, everything is solid. So this weirdness about water being higher density liquid than solid, it's only true for the liquid and solid right around the phase transitions that we know at room temperature. If you crank the pressure up super, super, super high, you always end up in a solid. It's just a different form of ice than we typically experience. Here's another phase diagram. You may wonder, what are two forms of a solid? Here's two forms of a solid we're fairly familiar with. Diamond and graphite are both different forms of solid carbon. And what's interesting to note here is you can see that this diagram has two triple points, and that could always be the case if you have more than one solid. There's only one solid liquid vapor triple point, but there could be a different triple point. For instance, this one has a triple point where the graphite and the diamond and the liquid carbon are all in equilibrium. Finally, let's look at a couple of questions to test yourself. So here's a phase diagram of CO2, and the question is, what is the stable phase at 20 atmospheres and 0 degrees C? So now you should pause the movie, answer the question so that the answer doesn't pop up immediately and you just convince yourself that you know it. Now I'm serious, you should really pause the video so that it stops, and then you answer the question, and then you'll see the answer. So the answer is the liquid phase. So if I go to 20 atmospheres, which I can read off of this has got to be somewhere between the triple point 5 and the critical point 73, and a temperature of 0 degrees C, which is sort of vaguely in between minus 56 and 31, I'm smack dab in the middle of the liquid phase. What about if I start at minus 105 atmospheres and I increase the temperature to 30 degrees C? How many phase transitions will occur? 1, 2, 3, or 4? Again, pause things so you can stop. And now, what's the answer? 1. If I'm at 5 atmospheres, I'm below the triple point. If I'm below the triple point, then I can only have one phase transition. I'll go from a solid, and then I'll sublime to a gas. Last but not least, if I'm at minus 100 C and 7 atmospheres, and I go up to a temperature of 35 degrees C, keeping the pressure fixed, how many phase transitions will occur? Here I have 2. Because first I start out in the solid, I move over at around minus 56 or something like that, I melt and turn into a liquid, and then, right around it looks like maybe minus 20 or something like that, it will boil and go from a liquid to a gas. And note, even though I'm going up above the critical temperature, we're not saying there's a phase transition between the gas and the supercritical fluid, because those changes are continuous. I don't notice a difference. When a substance melts, you can tell it used to be solid, now it's liquid. When it boils, you can tell it used to be liquid, now it's gas. When the gas changes density to the point where it's now technically a supercritical fluid, you can't notice that. There's no discontinuity, and so we only have 2 phase transitions.